And welcome back to the Server Virtualization Jumpstart, looking at our new technologies with Windows Server 2012 R2 and System Center 2012 R2. I'm Simon Perryman, Microsoft Technical Evangelist, and joined again by Corey Hines, President and Lead Architect from Hull Systems. Now, up to this point today, we've really kind of laid the foundation of building our infrastructure and then building our virtual machines that run on top of it. In this next section, we're really going to focus on networking, how we design and optimize our networks for our VMs so they can communicate amongst themselves and to our other environment variables. So what are we going to cover in detail then?
So we're moving on to networking. And networking is not much fun without networks. It's like multiplayer solitaire. It just doesn't fit. So we're going to take a look at a module on Hyper-V virtual networks, and this is the same sort of content that, again, like as we move into System Center, will bubble up in there, and because you do the same sort of management in System Center, but you can do it at a policy level across lots of hosts. What we're going to take a look at in here is how you'd basically define and manage the assorted types of networks that exist on a Hyper-V server, and then additionally take another look at network virtualization. Now, that's a big thing, and that's a big, complicated, scary thing. We mentioned it in the beginning. We're going to do a little bit on it right now from a conceptual level, and then tomorrow when you get into System Center, we'll actually see how you implement it within System Center, because it's not until you begin defining things like virtual networks and provider networks and ports and IP ranges and subnets that network virtualization becomes a tangible thing as opposed to a fuzzy concept. If anything virtual can be tangible. So this particular module, essentially three things: creating and using Hyper-V switches, some of the advanced features for networking, and then looking at using network virtualization at a conceptual level. So to begin, Hyper-V virtual switches. These are the things within Hyper-V that allow VMs and ultimately the host operating system itself to go connect to other resources on the network. So at the end of the day, you need something with an IP address, and the switch is what allows you to have that. And you think of Hyper-V virtual switches in the same way you think of physical switches. It's a layer 2 switch. So if you want to, for example, I've done this plenty of times in offices and home offices, not so much in big data centers, but I need another 10 ports because I've got 10 computers to plug in. You take a cable from one switch and you plug it into another, and you've extended the switch. And now you've got more ports to plug things into. That's what virtual switches are. It's a software-defined switch within Hyper-V that you can plug VMs into virtually, electronically, and give those VMs access to the physical, essentially the same resources that the physical switch that the host is ultimately attached to has. And so they're managed essentially by PowerShell or by Hyper-V Manager or by System Center, and you can have as many switches as you want on a Hyper-V host. There are no theoretical limits. There are practical limits. You start getting up to hundreds of switches, you'll start to see some issues. But from a production server standpoint, there's very little limitations on what you can do. Generally speaking, you will have one switch per physical adapter, or if you do teaming, you might have two adapters in a team and one switch for that adapter. So typically on a production server, you're not going to have that many, right? You're going to have one per essentially one to represent the extension of the physical switch into the different VMs. So if you've got 4 ports or 8 ports, that's about as many switches as you would traditionally see. Now, again, in the VM world, compares with the VM or vSwitch, not VDS. As you want on a... Wow.
Sound.
So let's take a look at essentially what the switch is and how we create it. So this little example right here is just a PowerShell snippet, right? So we can see that we're making 3 switches, okay? Now we'll talk about switch types in a minute, but what happens when I go to create those 3 switches is it creates 3 virtual network adapters within the host. So as you look at connections, as you create more switches, you're going to see additional connections appear on the networking connections of the host machine itself. So you can see I got 3 examples: management, storage, and live migration, and the corresponding created 3 virtual network adapters, each one representing the connection to that switch. There are 3 types of switches within Hyper-V. Okay, so if I jump out real quick to my Hyper-V console here, and I go to here we are. So I go to my virtual switch manager, and I go new virtual switch type. You can see there are 3 types listed: external, internal, and private. So it's pretty important to understand what the difference is between these. An external switch essentially connects me to a physical adapter, okay, or to a wireless adapter, right, which is, the reason the wireless adapter is there is not for your production data center that we run everything on wireless, but for primarily support for laptops running Windows 8.1, and because it's one code base, you get both in the server and in the client. So the external adapter represents a physical connection. The internal represent a connection between the host and the VMs only. So this is what we would have, traditionally thought of as a loopback adapter. So it can't talk to anything on the real network, but the host can see it, and the VMs that are connected to it can see it. And so this is often used in scenarios where I want to build up, a sandbox environment, maybe for development or testing, but I want the host to be able to see that environment as well, but the environment not necessarily to be able to see the internet. Or in those cases, I've seen folks use the host as a NAT device. So they put routing remote access on it, and they can do a NAT from the VMs out to the internet, so create a sandbox that way. And then finally, private is virtual machine connections only. There are very few reasons in a production world where you would use private. Those are primarily reserved for test dev scenarios where, when a couple of VMs, domain controller, DHCP, and all this stuff that, if it were to get on the real network, will create havoc, but I want to run it, so private switches are a way that's done. And it's constrained to one host and all the VMs on that host on that switch.
And I think, if you're taking the exam, you can definitely expect multiple questions on this. Here's a scenario, which is the best type of switch to deploy for that? So definitely familiarize yourself with those.
So here's a good kind of animated example of this. I've got a parent and two virtual machines. The parent has a physical adapter. The virtual machines have virtual adapters. Private switch, you can see the switch is created in the parent, but the parent has no access to it, only the virtual machines do. Internal, the parent gets a virtual adapter, and it can, using standard TCP/IP protocols, talk to both the clients and to itself as well. And you can optionally inject NAT, as I mentioned. And finally, external, the parent gets an IP, the virtual machines all get IPs, and it's actually bound to a switch. But what you'll find is that the physical adapter it binds to has no IP address. That adapter is limited to only the Hyper-V switch protocol. And it essentially expects to pass the IP address through to the virtual adapters, either on the parent or in the actual virtual machines themselves. So here's some examples of what that might look like. So if I create a standard network adapter, this is an external adapter. It's bound to a particular network card. Here's an internal one. You'll notice that it creates a network adapter, which is right here. Let me get my little guy right here. So it creates the network adapter right here, but it's not bound to any physical adapter. And then finally, if you do a private, there's no adapter created, but the switch is actually created itself, right? And so that's essentially what happens under the hood with Hyper-V. Whether or not it creates virtual adapters on the host determines what it can actually communicate with. VLAN tagging is something that is supported in switches across the board, and this is pretty key. Like, so if you're not used to working in large data centers, you probably don't encounter VLAN tagging a lot. But in large data center environments, everything's VLAN, right? This is standard practice on switches across the board, and it's important that when you're buying switches, if you're planning on doing VLAN tagging, you've got to make sure they support all the different scenarios you want, and make sure that they support, in particular, using virtual machines that are also VLAN tagged. You can't just put any physical switch out there and expect it all to work properly. You've got to make sure that it's enterprise grade, supports all the features that you want. So when we start talking about these switches that are, $5,000 versus $1,000, that's the feature set you're getting into, which is, per VLAN spanning tree, support for VLAN tagging for virtual machines, MAC address, multiple MAC addresses per VLAN. So you can have the same MAC address across multiple VLANs in some scenarios. So there's a lot of things you got to think about. But what VLAN tagging essentially is, it allows you to create virtual segments on a switch. So for example, if you have the first 10 ports on a switch tagged as VLAN 1, the second 10 ports on a switch tagged as VLAN 2, if you put a DHCP server on VLAN 1, anything on VLAN 2 is not going to get those packets. So it's a defined broadcast and communication domain that's mapped to particular ports on a switch. and every single port on the switch is mapped to a single VLAN. Some switches support multiple VLANs per port, depends on the operating system. With Hyper-V, you can define on, where are we to here? You can define on a virtual machine. I'm not going to do this because I wind up breaking myself, quite frankly. On a network adapter, you can define VLAN identification. The default is 2 if you turn it on. So the default's turned off, but if you turn it on, it defaults to 2. You can change this to any value you want up to, I believe it's 4096. And when you do that, all traffic that leaves this particular adapter has that VLAN tag on it. And as long as the switch honors VLAN tagging, it's going to make sure that that traffic only goes to other switch ports that have the same VLAN tag. And so you can have 2 VMs, for example, in the same host. You VLAN tag them. If they're on the same VLAN, they can communicate. If they're not, they can't. So it's a way of logically breaking up a switch. The whole reason people do VLAN tagging is because you don't want to have, you don't want to have lots and lots and lots and lots of different switches representing different customers and subnets and segments. You want to be able to use single larger switches and just logically isolate them.
Now, Corey, you being a hoster here, you obviously run lots of these kind of isolated environments where you'll have multiple DCs. What do you regularly do? I mean, have you kind of changed your methodology? Used to use VLANs, moved since then?
So our scenario is a little bit different in that we're creating disposable VM environments. So
they're temporary for a couple hours, right?
For a couple hours, at most a couple of days. So we actually use private networks extensively. To isolate VMs on private networks on hosts. And then if we need to cross-host, we can implement VLAN tagging to make sure that VMs on this host can talk to VMs for the really large scenarios where we want to span hosts on them. We don't use a lot of switch-level VLAN tagging in our infrastructure. We do it on some of our edge switches for we have a couple of different internet drops that come in, so they all come into the same pair of switches that are VLAN tagged and then aggregated together to distribution switches to different logical segments. So we did a couple of different ways that we take advantage of those things, depending on, and that's a pretty typical sort of configuration where you have an edge switch or a top of rack switch that everything kind of goes into, and then typically it's used for distribution, so you're not dealing with a lot of ports. So you buy a fairly high-end, powerful switch, usually 2 of them, make them redundant, and then you carve up that into different VLANs that represent different egress points for all the traffic. So it's fun stuff.
Nice.
So that's kind of the background on VLAN tagging and the different types of switches. As I said, as you create switches, we'll just do a run back here real quick and just kind of show you how I create some of these. So here's an example. So this is, you might remember Server 4 that I installed earlier this morning, or if you're watching the recorded version of this a couple of videos ago. We actually took this HV form, we added Hyper-V to it. And I don't think I rebooted it. Oops.
Uh-oh.
Let me just check and see real quick. I didn't reboot it. So let's go to HV3. We'll reboot this guy when we take our next little break here. And we just go into Hyper-V Manager. Let me close down some of these extra windows. Virtual Switch Manager. And so we'll just do an example of a private switch. Create virtual switch. We'll just call this one private. And I'm just choosing the type down here. I can set a VLAN ID on the switch if I want. This would be a switch level VLAN, which means all traffic on this switch is VLAN to a certain point. And we click OK on that. That'll actually create the switch. And I can then use PowerShell. Get VM switch, and it'll actually list all the switches that are there with the types, the names, everything of that nature. So very simple, management process to create them. And then as I work with VMs, I can then take any given VM and just by going through the properties of the VM, take an adapter and connect it to a particular switch. And you can change switches while the VMs are running. You don't need to shut them down to do this. Right. The final thing I'll add, which is not in our slide deck, but is a particularly important thing. And I've seen people take down their, not taking down their data center, but run into a lot of problems by ignoring this. Under a virtual switch manager, there's a little setting here called MAC address range. Now, this is really, really important. When you add a virtual adapter, so when you buy a physical adapter, and you may, I don't know if you remember this or not, but when you buy a physical adapter, the MAC address is actually predetermined. It's burned into the adapter. There's some adapters where you can change them through BIOS flashes and stuff. And the first 3 digits, or the first 3 bytes of the MAC address, generally represent the manufacturer, and the last 3 generally represent the serial number of the card. Hyper-V works kind of the same way. When you create a virtual adapter, obviously you can't stamp the MAC address in because it's virtual, so Hyper-V allocates MAC addresses much the way DHCP allocates IP addresses. And so when you create a VM, and for the first time, before you boot it, there's actually no MAC address allocated to the card. If I just kind of drill down in here and I go under Advanced Features, it's got no MAC address, and it's set to dynamic. When I boot this VM, I'll just turn this one on. So this is going to go nowhere. Oh, I got a fiber adapter card. So I may need to just remove that and reboot it. Just bear with me 1 second. Or I might get lucky. There may have been enough. No, it was. Let's just get rid of this fiber card.
Now, while you're doing that, one question that did come up is a question around network extensibility with these switches. If I have something like a packet forwarder, can I go and forward that information? And you can. The Hyper-V switch is extensible, so we do try to work with our partners and forward things over to Netmon, Five9s, all of these kind of packet inspection extensions you can use. So that's fully supported.
So I've turned on this VM here, and there's no operating system. So we talked about installing operating systems earlier, but turning it on is actually enough to get it allocated a MAC address. I'm just going to power it off again, and we'll go look at the settings of it. And we'll go down here under Advanced Features, and you can see it's been allocated a MAC address. Now, look, if you pay attention, 00155D, 317100. Okay, so I don't expect it to be, that'll be on the test, right?
Uh-oh, memorize
What
that.
was the MAC address of Corey's server? 387100, remember that. The 00515D is kind of the generic Hyper-V manufacturer code, but you can change it. But point being, this now has a MAC address, and that MAC address falls in the range from specified on this particular server. Now, if you look real close, I took the first MAC address in the pool, right? Now, the reason the other 2 servers didn't is because they actually were migrated from another machine, so their MAC addresses were already set. But I took the first address in the pool here. The second VM I create would take the next one, and so on. And what Hyper-V does is it allocates MAC addresses out. Now, if you look at this real close, you say, well, if you do your hexadecimal math in your head, it's only 256 addresses here. So does that mean if I try to, what happens when I try to start 257 VMs? The answer is it'll fail. Where does this number come from? The number comes from the IP address of the machine when you installed Hyper-V. So that means that by default on a Hyper-V server, if you were to set up all your machines with the same initial IP address, like you might in a build lab before they go into production, they'd all have the same MAC address range, and you'd wind up with 2 machines with 2 VMs with the same MAC address. That's happened to people, right? It's up to you as the administrator to modify this MAC address range so that it doesn't conflict across all the different servers. You start thinking, well, that's really dumb. What a horrible thing to have to do. And the answer is you're right. But if this is managed by VMM, VMM manages the global MAC address pool. So if you have a lot of Hyper-V servers, this right here alone is one of the reasons you would want to put VMM in place. Because you don't want to have to worry about MAC addresses all across all your different Hyper-V servers. You want to put VMM on top of that. You can set this through script if you want, but this is set as a fixed range based on the initial IP address of the machine. And like what we do, for example, on our servers, is we immediately come in and just go, we just do this. And we make it huge.
Okay.
Right? So you have much less of a chance of and you can actually change these as well. And what we do when we're trying to track down MAC addresses, so for example, in our hosting infrastructure, we don't use VMM to manage the hosting servers because of the turnover rates. It doesn't work for VM. We use it to manage all the deployment stuff. But in ours, we use the first digit to represent the server the MAC address comes from, and then we give it a really big range, and it works fantastic.
Nice.
So you can muck with this and play with this and do all kinds of fun stuff with it. Or you let VMM take care of it for you. So I just want to make sure I point it out because I've seen people in the past get in trouble by just kind of forgetting about this. So some advanced networking features, just kind of talk about a couple of different things in here. You may have noticed within the settings of the network adapter a couple of different settings. ARP, neighbor discovery positioning, DHCP guard, port ACLs, trunk mode, and then network traffic monitoring and bandwidth limit and burst support. To kind of explain what these mean, have a look at the settings of a network card in a VM. And so we can look at the different settings in here. So we'll start with bandwidth management. Just like we did storage IOPS earlier, storage IOP limiting, this limits the bandwidth of a network adapter to a certain amount. So for example, you can have some VMs limited to 1 gig, some VMs limited to 10 gig, some maybe 100 meg or 10 meg, whatever you want to do. So this is just standard QoS for network traffic on the VM. Under advanced features, MAC address spoofing will actually emulate the MAC of the host machine. Okay, so there are scenarios where that may be necessary if you're running a firewall device or something of that nature. DHCP guard is pretty straightforward. It prevents DHCP packets from leaving the server. So someone can't set up a rogue VM with DHCP.
Now, why would that be bad? Ultimately, they could go and redirect those packets somewhere else, right? Steal information?
Well, if you have a rogue DHCP server on your network, that's a world of hurt right there. There's no easy way to get out of that.
Well, we should also not necessarily consider that people are doing that maliciously. You could have a developer that's going and setting up their own environment. They weren't correctly isolated. That could cause that type of problem. So definitely a nice security feature that's built in here.
So move this virtual machine to another cluster node if the network disk is disconnected. So again, if it's cluster aware, it'll actually migrate the VM if it detects a network fault. And then finally, you can enable port mirroring. And what port mirroring does is allows you to do network traffic analysis by having a VM that monitors the traffic of another VM. So for example, if you're doing advanced troubleshooting, so why my application's so slow, you want to do a packet capture. The way that most network analysis folks do packet captures is they take an old hub, a dumb hub, and they put it between the host and the switch, and they plug into it so they can see all the traffic. This emulates that sort of functionality. So you can monitor network traffic. And then finally, you can do NIC teaming. We'll talk about teaming in a second, but you can enable the adapter for NIC teaming, which passes the connection state of the actual physical adapter into the VM. So the VM can detect if you pull a cable or not, which is a nice thing to have. You have a VM where you want to do teaming. So you were mentioning a second ago virtual switch extensibility. One of the neat things about the Hyper-V switch is that you can extend it to do different things. And so, for example, there are companies out there that do this. I believe the Cisco Nexus is one of those, where they inject filters into the switch that allow you to do advanced filtering of network traffic, advanced monitoring of network traffic, and just take that Hyper-V switch and make it more powerful than what it is. So this isn't something that the average admin is going to do. You may buy a product that does Hyper-V switch management, and it does so by injecting a layer into the switch to give it advanced functionality. When you do when you work with Virtual Machine Manager, Virtual Machine Manager actually does this. So it interjects a Virtual Machine Manager switch extension that allows you to create virtual adapters and pipe them through single physical adapters to give the switch more capability that's only available through VMM. So it's this is present, it's available, and as you get products and as things evolve, you'll be able to add extensions to the switch to get different functionality. SRIOV. A little drink of water real quick. I'm getting dry here.
Stands for single root I/O virtualization.
Good timing. SRIOV is a way of passing calls directly from the NIC into the actual VM.
Skipping the hypervisor layer?
Skipping the hypervisor layer entirely, going around it and straight into the NIC. So this is something that you would do on very high network throughput VMs, okay? Very high network throughput VMs. So for example, that database that's handling tons and tons of transactions, and you want to get the highest possible network performance. Higher throughput, lower latency, reduced CPU overhead by essentially bypassing the parent and paging that data directly into the switch in the VM. So it's not something you really have to configure. You need an SRIOV enabled network card. You typically turn that on through the properties of the NIC, and then on the VM itself, on the switch, sorry, on the switch, but on the network card, under advanced features, or sorry, hardware acceleration, you would enable SRIOV.
Now, as a hoster, do you actually use this?
No.
Is this something that you would think about with future acquisitions?
No, it's not, because we're not running VMs that require high network throughput.
They're generally local, right? That kind of isolated environment within the host.
So, if you want an example of what might be this, let's say you have a file server in a VM that's holding user profiles for 1,000 users, right? Very high throughput VM. You have an Exchange server in a VM that's got mailboxes for 10,000 users. You've got a SQL database or a SharePoint site. It's an application role in a VM that's passing a lot of data on the network and handling a lot of connections. And you just shortcutting the path so that you're not going through the parent partition's driver model into the VM, you're going around it and straight into the VM. But you require SRIOV enabled network card, which most of them have that capability, quite frankly. There's very few that don't. You just have to, by default, it's typically not turned on. You just enable it on the NIC and away you go. And the only gotcha is that if you're going to live migrate a VM and it's an SRIOV enabled NIC, you've got to make sure it's on the other side as well, or it won't work. So it's something you just enable across a cluster, for example. Virtual machine queue. This is another very similar piece of functionality to SRIOV in terms of concept, in that it allows data to be paged directly into the VM. It's essentially shortcutting the path. This is turned on by default on all network adapters you add to VMs. It's not necessarily turned on by default on all network cards, but once you turn it on, it's simply going to be used. And it allows the CPU load in particular to be reduced on the host by just bypassing some of that host stack going directly into the VM.
So a good example might be, a high CPU intensive application is running inside a VM, so you want to kind of offload some of those CPU cycles from the host over onto the network.
Absolutely. Again, these are functions that can make throughput better, where there's nothing you really got to do to configure them other than turn them on or off. And if you turn them on, the operating system, Hyper-V, knows how to figure this out and make it work. And so, as I showed earlier, this is where the advanced features live, just under the settings of the switch. And then finally, before we move into network virtualization, talk about NIC teaming for a little bit. So NIC teaming is a way of, and this is a very old concept, there's nothing new here. It's a way of taking two network cards and pairing them so they act as one, right? Just like you want fault tolerance in your storage channels, you also want some fault tolerance on your network. There's basically three fundamental ways that you can do teaming. There's link aggregation, which you can take, two 1 gig ports and you aggregate them into a 2 gig port. Requires the network card and the switch to communicate together to treat it as one channel. You can do standard, what they call switch independent teaming, where the operating system teams them together, but the traffic only goes over one of the two cables, essentially. And if one of the cables fails, it seamlessly goes to the other cable. So it's redundancy, but not a performance throughput. And then there's other variations that are, kind of vendor specific, that do different, variations of link aggregation, of standby, active passive type cables. And you can go upwards of, there's like 32 cables to a single link. The one thing that teaming doesn't do is make data necessarily go faster, right? Because a 1 gig cable is still a 1 gig cable. However, in the past, when you wanted to do NIC teaming, this is 2008 R2 and sooner, you needed drivers from your network card vendor to do this. That is no longer the case. Now, if you have a network card, you have two network cards, you can team it directly within Windows. And so to kind of show you how this operates and how simple the teaming is to actually do, let's go over here to server 1. What I'm going to do is just shut this guy down and add a second network card. Adding a network card is not something that you can do while the VM is actually running. So we're going to shut this guy down.
Now, I think, to kind of add to what you were mentioning here about the inbox NIC teaming, this is driving down some costs for our customers as well.
Absolutely.
In the past, when they had to learn this NIC teaming software, it could be kind of complicated. And so there's often a lot of vendor lock-in and investment in training just how to use these particular driver models, this teaming software. So now that we've kind of standardized it, almost virtualized it conceptually, it's much easier to do it using these inbox tools.
Absolutely. So what I'm doing here is just adding 3 network adapters to this server. And this is the Generation 2 VM, so I can only add synthetic adapters. I'm going to boot it up. So once this guy boots up, we're going to go ahead and log on to it and configure a network team. So that's all I've done. Just multiple network adapters. These can be, these can be virtual adapters in a VM or physical adapters on a host. If you go down the road of using virtual adapters in a VM, and there's a lot of theory around, kind of how should you team things? Should I team the host? Should I team the VMs? And this is kind of the way I describe it. If you have two cables going to a switch on a Hyper-V host, it's worth teaming them. If you have two cables going to different switches, what you would do is create a Hyper-V virtual switch for each interface, go into each switch, and then team within the VMs. So that if either switch goes down, the team within the VMs will actually take over and keep the link up. And you would check that box on the settings of the VM to say that the interface is enabled for teaming, so that the link state, connected, disconnected, up, down, can be passed to the VM, so the VM knows, hey, the actual physical link went down, and can respond in the team accordingly. So we're going to go ahead and connect to this one. Let me, once again, because of the screen resolution, drop this way down to itty bitty. And we're just going to log on here. And so teaming's a piece of cake to configure. We're just going to go into Server Manager and do it. Let this guy boot up. Server Manager should fire up for me.
Now, we did have a question come in, kind of asking how these virtual network adapters and virtual networks interact with firewalls. They just work with Windows Firewall and same way, no special considerations here.
There's nothing special about them, right? It's just an adapter. There's nothing special. And then when you make a team, it creates an additional teamed interface on the machine, and that just becomes the one that you configure. So I've got Server Manager up here. I'm just going to go to my local server area. And this is just still taking a second to settle down right after I boot the machine. So we'll let this collect up here. Yeah, so nothing special on the firewall, nothing additional you've got to do. You would just manage the interface a little bit differently. So if I go down here under network teaming, so there's my adapters that are all DHCP enabled. You'll see NIC teaming is disabled. Click on that disabled link. It's going to open the network teaming configuration tool. And I just go Teams, New Team. And I'm doing this in a VM, obviously, but you could do it on the host, right? The process is the same. Check the three adapters. My team. Because I'm in Seattle, I call them the Seahawks.
Nice. Good to have a winning team up there.
Yeah, that's right.
Where are you from, Tampa?
We're not going to go there.
We got an international audience. We won't go too many football jokes here.
Yeah, we'll just get laughed at. So that's going to go ahead and create the team, and you'll see it's now kind of querying the status, trying to figure out what's connected, what's not connected. And this one, this one, in all fairness, is not going to work 100% properly because I haven't configured it as a pass-through team. So what I need to do is come down here under each of these adapters, under advanced features, enable this to be part of a team, enable this one to be part of a team. There we go. All right, so now it's actually picked everything up. And so I've got a 3-adapter team. It's showing all links as active. The team is up. And if I look at the actual network adapters now, so I'm just going to refresh Server Manager. You'll see an additional adapter appear down here, which is the team. And you'll see the other adapters kind of went away, right? Because now the only adapter that we're really concerned about is the teamed adapter. If I look at the actual network connections, here's the team. Here are the actual physical adapters. But when I want to configure things like IP addresses, this is now where I do it. I do it on the teamed interface, not the adapter interfaces. So this is where I configure things like a static IP or whatever the case might be. On the teamed interfaces, if you look at those, all they've got on them is this Microsoft Network Adapter Multiplexer protocol. So they've had everything else removed because they're managed adapters as part of a larger network team. So there you go. That's how you essentially configure teaming. Now what I've done here is, quite frankly, pretty dumb because I've teamed 3 adapters plugged into the same single cable. It's not
Oh, yeah, I mean, that was still pretty simple to set up. There's actually a pretty funny comment that I'm just reading coming through here saying it was harder to actually break our old team than it was to go configure the new team, just to go use that new feature. So as you can see, pretty straightforward to implement. And again, regardless of the underlying actual NIC or hardware manufacturer, we support all the different APIs, all the different
I can mix Broadcom NICs, Intel NICs, 3Com NICs. Are there still 3Com NICs?
Who knows?
I don't know. I primarily use Intel NICs, so some Broadcom, but primarily Intel. So yeah, you can mix manufacturers. You can even mix 10 gig and 1 gig, but don't, because it won't. Just don't. Same speed, same. Ideally, as similar as possible, because you want all links to behave the same. And like I said, what I've done here is inherently stupid because I've got a team of 3 interfaces plugged into 1 cable. What I would ideally want in this scenario is I would want three external switches, each going through 3 external physical cables to bring the team all the way into the VM and have it actually protected from one of those links going down. So that's pretty much what that's all about. But wanted to show the example of how you actually configure it.
Cool. So that's really covered kind of the host networking pretty well, and even kind of extending up to our virtual machines a little bit. But now we're going to kind of move on to a new concept and talk about network virtualization.
Yeah.
So I guess let's kind of kick it off. Why do we care about this?
Well, we care about it for this reason right here. So this is a really complex animated slide where little colored balls are going to slide around. Okay, but put yourself in the position of either a hoster or a company that has acquired another company needs to bring them in. In either way, you have, say, multiple logical subnets that need to cross around your data center. So I have, a 10 dot subnet over here that needs to talk to a computer on the 10 dot subnet over here, 4 switches down the chain, and there's another 11 dot, and these, we had isolated traffic crossing switches. That's kind of the scenario, right? Isolated traffic crossing switches. And if you look at this, I have 3 VLANs. I've got kind of red here, I've got kind of green here, and I've got kind of sort of a bluish purplish color there. And I've got different servers that are on different colors. And so what you're seeing here is this green server can only talk to other green servers because the switches, as you can see right here, have been configured with the same VLAN ID. So every hop along the way has to understand the VLAN. So let's look at a scenario here now where, I want to erase a little area. I want to get rid of some of this. A scenario where I'm adding another server. And because of physical limitations, rack space and cages and whatnot, this VM comes over here. Now what I've got is a scenario where, let me get my pen, where I've now had to add additional VLAN information all across the board to make sure that these 2 hosts here can talk to each other. All right, let's look at another really bad example. I add another host all the way over here. Now look where I've all the edits I've got to make.
A lot of things happening, huh?
Now, look at all the potential to screw things up and take everything down. Right? When you start messing with things like VLANs and whatnot, it's scary. Like, anyone who does that will tell you they're terrified. And how do they manage it? Most of them do it with Excel. Massive spreadsheets. Remember the days of managing static IP addresses. If you create a conflict, something bad happens. Well, it's amplified if you screw up or mess up VLANing and you take half the data center offline. Very, very tricky stuff. And so the result of this is, managing VLANs, not only do you have a limited number, but you've got to update them constantly. You've got to track where everything is because it's port specific. Port goes down, I'm going to move it to a new port. Is it on the same VLAN? Am I going to inadvertently plug, Pepsi server into Coke's VLAN, and all of a sudden the recipes are going to cross over and wind up with Mountain Dew or something? I don't know. So that's kind of the problem. Software-defined networking is the solution, where we don't define things at a physical level, we define things via software and via policy. And what that allows us to do is say, we don't care about the physical, we only care about the logical. We only care about, what is this host or this VM logically contained? What is it logically allowed to talk to? And rely on software to govern everything else. So what that means in real terms is we're allowing Hyper-V, because this is all with network virtualization. These are VMs running on Hyper-V servers. And we don't worry about VLANing switches. We let Hyper-V figure out which VMs on which hosts are allowed to talk to which VMs on which hosts, and take care of isolating the networks that way. Now, the way Hyper-V is going to do it is using generic routing encapsulation. So here's I'm kind of jumping a little bit ahead of myself, but here's kind of what it looks like in practical terms. So in this example right here, I have two customers, right? So I've got a blue customer and I've got a red customer. Okay, so you can see them right here. They need to talk to each other, but they're on different Hyper-V hosts. And if you'll notice, they've also got the same logical IP range. Now, you start thinking, well, how would you make this, two machines with the same IP address on the same host talk across the real network? The answer is the only way you could really do it is VLAN things, which is lots of cables. But what network virtualization does is allows you to take all those IP addresses and create what are called mapping. So the host tracks what the IP addresses of the VMs are, what the IP addresses of the hosts are, which VMs are on what hosts, and builds what is essentially this type of routing table. And says, hey, you want to talk to, if 11 wants to talk to 12, 12 is over on this interface on another server, and is able to take that packet, wrap it in a generic, an additional TCP/IP packet with routing information, figure out which host it's on, and ship it over there. And this is all possible through Virtual Machine Manager. So Hyper-V has these, inherent routing tables, is a good way of thinking about them. Virtual Machine Manager keeps them synchronized across all the hosts. So when a VM wants to send a packet to another VM, Hyper-V knows which virtual network it's on, which host owns that virtual network, and where to route the actual packet. So in effect, the host acts like a big NAT device. You want to kind of, one way of kind of thinking about it. And it's all governed through policy. And the policy comes from Virtual Machine Manager. Okay. Now, I know this is a very conceptual topic. It's somewhat confusing to understand, and I totally get that and I totally understand that. Where it'll hopefully begin to, to kind of gel together is when you start looking at the actual objects you create in VMM. So when you define, for example, a virtual network, and you say, here's the hosts this virtual network is allowed to live on, and here are the ports that virtual network's allowed to connect to, and is it a network virtualization enabled virtual network? So when you create a VM, that's all turned on by default, and it just figures out where to send everything. And the key here is that when virtual machines move around, this is all updated. So when a VM is running on a host and you say live migrated to a new host, part of SCVMM managing that live migration is it goes and updates everything. So that now that particular IP address, maybe of this SQL server, is now on a different host, and all the network virtualization, quote unquote routing tables get updated accordingly so it knows where to send that data.
So good questions kind of covered here. What are the components actually used to manage this? Is there any hardware involved, or can everything be software based?
Everything is fundamentally software based, right? So there's the only hardware piece that would be involved would be a network virtualization gateway. And
that's optional whether it's hardware. You can have virtualized ones.
So what I mean by that is the network virtualization gateway provided by Microsoft is a VM and a host combination. So you have a certain Hyper-V host running the network virtualization gateway that's able to talk to assorted virtual networks and then route that traffic out. Or you can get hardware-based network virtualization gateways. So there are some hardware companies that actually manufacture these. But otherwise, no, this is 100% software-based. So you can create a, whatever switching fabric you want, and then you define a virtual network that is across all the hosts in your data center. And then when you create a new VM, you simply say, this VM's on this virtual network that all these hosts know about. And so when that VM goes to communicate on the network, if there's another VM on that same network on another host, the routing tables know that 10.1 over here, 10.2 is over here, 10.2 is on host A and is able to route the traffic to host A and then into the virtual network again. So every Hyper-V host acts like a mini NAT device that's publishing everything and bringing everything in. And GRE is the generic routing encapsulation, industry standard protocol for just putting a TCP/IP packet inside of another one for the purpose of shipping it somewhere, is used to move the data around. It doesn't incur overhead, a tiny bit, not a lot. Certainly it doesn't outweigh the complexities of not having this in place. So that's the basics of network virtualization.
Alrighty, well, we have just about wrapped up this chapter now, so we're going to go ahead and take a 10-minute break. After we return, we're going to go and look at Hyper-V VM mobility, so things such as live migration, as well as Hyper-V replica, being able to do point-in-time replicas of our virtual machines for DR.
Really cool stuff coming up.
Very cool stuff, so stay tuned. We'll see you shortly.